Okay, today we're going to build off our lesson 19, which was the original first definition of the derivative, and we're going to see two different definitions of the derivative. They're the same ideas at heart, just a lot of differences, small differences in notation. Okay, so remember the whole idea originally that we talked about is that the derivative finds is instantaneous rate of change or tangent slope. Okay, now we find that derivative by taking the limit of the average rate of change, or the limit of the secant slope, which is slope between 2 points. Here we go. This here was what we learned in set 19. Let's talk about it, all right? The idea is you want to know at some point, now let's start with saying there was a specific point you wanted to find how fast is the curve changing at that point. Now, theoretically, I mean, I don't care what the curve, some unknown curve is changing at, but to find instantaneous velocity or how fast population is changing at an instant, this has a lot of applications. So always remember, we're going to get to those applications, but for now it's going to be a little abstract. We'll get to the uses of it soon, but first this technique, all right? So I want the change at A, just at that instant. You start by taking another point a little bit away. Now let H be a distance away you're going to go to get to a second point. We can only really draw a line through 2 points, so we need to get a second point. Now if I started at A, went H over, that puts me at A plus H. That then would be another point on the curve. Those have corresponding Y values. F at that A and F at A plus H. And the whole goal is change, or ratio of change between the two. That is the slope, change in y over change in x. That green line is the secant line, the change between 2 points. Now if I just take this little gap smaller and smaller, then if I went a little less farther over, then I'd get a secant line like that. And if I went a less farther over on the curve, I'd get a secant line like that. And a little less, I'd get like that. I would start to approach, as h gets small, I'd start to get change at A. Right? Now then, the first part of the first derivative is used to find the tangent slope at A. Some actually named point, like at 2 or 3. What's the slope at 2? What's the slope at 3? Something like that. A stands for an actual number. Now the slope between those 2 points would be change in y over change in x. The change in y is the change in the f values, f at A plus h minus f at A, the difference in the y values, over the change in x values. Now that's change in x is A plus h minus A. But A plus h minus A leaves us just h. And that represents the slope between the 2 points. We don't want those slope between 2 points that are way apart. We want to get the points close together. That's the whole idea of instantaneous rate of change. Now we get them together by taking a limit. Okay, now that is just the slope between 2 points. If I'm going to take the points closer and closer and closer and closer together so I get the slope at A, then I get those points closer and closer by taking the gap, which h stands for the gap, or the distance we went over, to nothing. I take the gap down to nothing by taking the limit, or what happens to that slope as h gets closer to 0. As h gets closer to 0, I start to approach the slope at the point, or the tangent slope. So the limit of the slope between the 2 points is the derivative. Now we talked about notation-wise the other day, how the notation for the derivative of f is f prime. That means the derivative of f. Then here you would either say it's at any x, so a rule, or at a specific point. Now here we found this slope specifically at a. So when I find this, this is actually a number, a true numerical slope. There's only one slope at a, so it would be some number. All right. Now, consider, however, if instead of finding the slope specifically at some a, you wanted the slope at any x. So you wanted a rule that could find the slope at any point. In that case, then, instead of at a, you would just pick any x, and you would have a point there. Now, you still want to create a second point. You can only get slope through 2 points. So we're going to let h be the distance to the next point, which puts me at whatever x was to start with, plus some unknown h. The y's for those, then, would be f at x, and f at x plus h. All right, now, the purpose of this, then, will be find a rule for slope at any x. That's what we're trying to accomplish here. Now, the slope at any x, again, notation-wise, would be the derivative of f, but instead of at a, at any x. All right, we still are going to do this by finding slope between the 2 points. So we're still going to find slope, but this time, instead of a's, we're going to have just generic x's. The change in y is f at x plus h minus f at x. The change in x is x plus h minus x. X plus h minus x leaves you with just h. To get the points closer together, once again, we take the distance between the two, h, down to 0. What happens as h goes to 0 in this slope calculation? By doing that, that's what found as the derivative or the tangent line slope at some point. Now that was the definition, or the first definition of derivative. Today we're going to talk about two other forms of derivative. And they look a little different notation-wise, but again, it's the same kind of concept. Imagine the alternate definition. And the alternate definition is used to find the slope at a particular point, at a specific a. Right? I still want to let a be some point I want the slope at. And the goal is to find what's the slope at that point, the tangent slope. We still need another point. Now here's where it gets different. Instead of going some distance over h, we're just going to let this point be some other point on the curve. X is just some other point on the curve that I can use to draw the slope through, and so it has an x and a y value. Now I still want to find the slope between those 2 points. The slope between those 2 points, the change in y is f of x minus f at a. Here's going to be a little different. The change in x, or the difference between the two x's, is x minus a. So when you see, rather than an h in the denominator, an x minus a in the denominator, you're going to know you're dealing with the alternate definition right away. Now, another difference besides that different looking slope is the limit. Here, over here, we had a gap that we made smaller and smaller, and it got the points closer and closer together. We're still going to take the points closer and closer together, but we're going to do it differently with the limit. Now, a can't move. It's a constant, so it doesn't go anywhere. But in terms of what can move, x is a variable, and so I could choose an x that's closer, draw the slope, or closer, draw the slope, or closer, draw the slope, and I would start to approach the slope at a. So now I'm going to do that by choosing x is closer and closer to a, so I want to say what happens as x approaches a. If I do that on the slope of the 2 points calculation, or the secant slope, I get the derivative at a. So that is just another way, like the first problem, of finding the slope at a specific point, the alternate definition. So you have two ways to find slope at a specific point. Now, last definition, I promise, there's no none after this, is the symmetric definition. The idea is that rather than approach one point from one side, you approach one point from both sides. So 2 points are going to move. So let's say we just wanted the derivative at some x here. It's going to use a gap again. So we're going to create an h above, which puts me at x plus h above. But what's different is that we're going to create a second point. Symmetric means same on either side. So if we create a second point, the exact same distance on the other side, then it would be x take away an h. I'm still going to draw between 2 points. Now, we're going to move both points together. When I move both points together, then draw the slope and draw the slope, then I start to approach the slope at x. And I'll get the same answer, although it looks different, but I'll still get slope at some x. So it's used to find slope at some x, but it approaches from both sides. All right, now in terms of the slope calculation, this y value would be f of x minus h. This y value would be f of x plus h, or is f of x plus h. So when I go to calculate the slope, change of y is f at x plus h minus f at x minus h over change in x. If I take the difference between these two, x plus h minus x minus h, that's the change, you'll see the x's subtract away, and you'll actually get 2 h's. Now that makes sense because you have 2 gaps of h on either side, so it's a total difference of 2 h's. Now, if you then take the points closer together, you're going to take the points closer and closer together by taking that distance between the points h down to nothing. So we're going to take the limit as h goes to 0 of our slope, or difference quotient. Simplify this into 2h, and you've got, again, a rule for the derivative or the slope at any point x, right? So it's all about taking slope between 2 points and getting the points close together. Just differences in how that's done. Let's move on and see how this works. In this case, I want you to do a little compare and contrast, all right? I have 2 ways of finding the slope at 1 of the same function. You can see it's the same question. Find the derivative at 1 for the same function. We're going to do it 2 ways. The first definition would be to say the limit as h goes to 0 of f of. Now remember, in that first definition, at a specific point, we're looking at having more like an f of a plus h minus f at a over h. This is at a specific point. So I'm going to do that approach, f at a plus h minus f at a over h. Let's start by identifying a. In this case, the specific point I want the slope at is 1. So it would be the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. Now, let's use the function. Before, we didn't actually have a function to work with. I was just doing general. But now, every problem, they'll actually give you a specific function that you use. Now, this function says that you are supposed to take 2 and subtract whatever you put in squared. So f of 1 plus h would mean take 2 minus something squared, whatever you put in. And in this case, what you're putting in is 1 plus h. This part's done. Minus f at 1. F at 1, again, it's the function 2 minus whatever you put in squared. Then look inside the parentheses for what you're putting in, and what you're putting in is 1. Underneath is h. It's not f of h, it's just h, so you're not putting it in anything. It's just a straight up normal old h. That's the part that students starting out tend to make the most mistakes on, is making the jump to the function and what that looks like and what you put into the function and where does 1 plus h go. That's the hard part. Let's continue on. Let's simplify. So we can take the limit. If I simplify, I get 2 minus 1 plus 2h plus h squared. That's still all that first quantity minus that second quantity is just 2 minus 1 over h. I don't know if I really needed those brackets anymore. Now, simplify. I'm going to go, I don't know if it's too fast here. If you look at the constants, we have 2 minus 1 minus 1. Well, all together, then those would drop out. So that's going to be gone. What is left is if you distributed the negative, you would have a negative 2h minus an h squared all over h. And again, the 2 minus 1 and the minus 1 go away. If you continue, the limit as h goes to 0. They all have an h, so we can factor out an h and divide out that h. At that point, we're golden. Direct substitution says that if h goes to 0, this approaches negative 2. Now, take a second to figure out what the heck we just did. We pushed around a ton of symbols, and we got negative 2, and what does it mean? Well, the function is 2 minus x squared. We know that's a parabola opening down and shifted up 2. So the parabola, the graph of this function for this problem looks like this. When I wanted f prime at 1, that means find the slope at 1. Well, here's 1 about. And so when I found the slope at 1, there it is. Well, that negative 2 represents that tangent slope, or that slope just barely touching at 1. The slope is negative 2. I don't know about the scale negative 2, but the sign definitely makes sense. I know it's a negative slope, so that looks good. Let's try then the same question, but comparing it to a different way of finding that slope, the alternate definition. The alternate definition is more the idea of x approaching a. And we use that point A, but this time we're going to approach differently. We're going to let no gap of h. We're just going to let x be some other point on the curve, and we're going to get x closer and closer and closer to a. Now, again, idea a in this case is 1, so this would mean the limit as x goes to 1 of f of x minus f at 1 over x minus 1. Good enough. Now, let's go the function. The function is still 2 minus x squared, so if I put in that function here, this would just be 2 minus x squared. F of 1 is 2 minus 1, or 1, over x minus 1. The limit as x goes to 1 then of 2 minus x squared minus 1 is 1 minus x squared over x minus 1. Now, the whole time I want to do the limit eventually, but right now you can see that I'm getting 0 over 0. That's pretty much the case for all derivatives. Remember, you're taking infinitesimally small change between 2 points. And yeah, the change in y is going to approach 0, and the change in x is going to approach 0. So every derivative is going to have that 0 over 0 issue you're going to have to deal with. In this case, we could do some algebra. I could factor a little bit and get 1 minus x and 1 plus x. Unfortunately, though, doggone it, these don't quite cancel. They're not quite right. So in order to get those to cancel, I'm going to try and make the signs the same. I could make the signs a couple different ways, but I'm going to factor out a negative 1. If I do that, then it becomes positive x minus 1. And then I can divide out an x minus 1. If at that point then I direct substitute, I get negative 1 times 1 plus 1, or negative 2. I get the same slope. Either method, it's the same idea. It's just a little different algebra along the way. All right? That's the point. Now then, say we look at another compare and contrast. If I wanted the general derivative at any x for this function, just kind of thinking my way through what I would expect in this problem. There's x cubed. X cubed plus 1 would be shifted up 1. Now, looking at that graph, I would expect slopes to always be positive. So when I go to find the derivative, which is a rule for finding slopes at any x, then I would expect a rule that only gives positive answers. Let's see if that pans out. So, start with the first definition. This time it's at any x, so it's f of x plus h minus f of x over h, not f of a plus h, because there's no a here. Right here, this tells me they want a derivative at any x, not at a number. So there's no a's here. Going on then, if I use the specific function here, then f of x plus h would be cubed plus 1, and because that's what the function says to do, and instead of putting an x in, I'm actually putting in an x plus h minus f at x, oh geez, there's f of x right there, x cubed plus 1 all over h. This is going to require a little bit of work on my part. I need to expand x plus h cubed. That's x cubed plus 3x squared h plus 3x h cubed plus h cubed, if you remember your expansion of cubes, plus 1 minus x cubed minus 1 if you distribute. The x cubed subtract away, the 1 subtract away. After that, you can see that everything has an h. So if you factor out an h, you're left with 3x squared plus 3x h squared, oops, this is squared, plus, which means, sorry, I made a mistake. My bad. This should have been 3xh plus 3xh squared plus h cubed. The h's should grow in power as we go. So if you took an h out of that, you're left with an h. And if you took an h out of that, you're left with h squared. All right, sorry about that. H's divide out. Now you can evaluate the limit. If you let h go to 0 and what's left, this goes to 0 and this goes to 0, and all that's left is 3x squared. Now that's the derivative of x cubed. The derivative of x cubed plus 1 is 3x squared. That kind of makes sense. We said we should get a rule that has or makes positive slopes, and 3x squared would do that. It makes positive slopes because squares are always positive, or 0. All right? So, seems like that's working. If I could use that rule to find the slope anywhere. If I wanted, hey, what's the slope at 1? I could put 1 into my derivative, and I'd say, oh, the slope at 1 is 3. And if I wanted the slope at 2, I could put 2 into my derivative rule. And I'd say, oh, the slope there is 12. And that would be logical because the slopes are getting steeper and steeper. All right, so a derivative rule is a great thing. It allows you to find the derivative or slope anywhere. Let's go and use the symmetric definition, which we just learned, and see how it compares. It's the same function. It's still at any x, and so it should give the same answer. Let's see how it goes. The symmetric definition, as we just said, is to approach from both sides. H above x and h below x. The total change in x on the bottom of the slope, rise over run, is 2 h's. The run is 2 h's. If I use the specific function, the limit as h goes to 0 of f of x plus h. Here's the function. It says cube it, add 1. In this case, they're putting in x plus h. That part is done. Now I need to do f of x minus h. Well, if the function is cube it, add 1, in this case I'm adding x minus h, then that's that part, all over 2h. Just like over here, I need to do some cubic expansion. X plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed minus plus 1. Plus 1. The next part is x cubed. Now here's where it's going to get hinky here. Really it's a negative h. So negative h to the first is going to be negative 3x squared h, then positive 3xh squared, then negative h cubed, and still plus 1. Now if you're thinking, man, I could not do that binomial expansion by myself, I don't remember that, don't sweat that too much. It is not a big idea of calculus. It is a pre-calculus idea that you really should know, but if it don't, it won't kill you. So here we go. Let's simplify. X cubes will subtract away. The 3x squared h's do not subtract away because it's minus a negative. So it's positive 6x squared h. The 3xh squared and the 3xh squared, those do subtract away. H cubed minus negative h cubed is positive 2h cubed, and the 1's subtract away. All that over 2h. Let's clean it up by factoring and canceling. If we factor out in the denominator, the numerator, a 2h, then we'd be left with 3x squared and an h squared. If those two h's divide away, we have the limit as h goes to 0 of 3x squared plus h squared. Well, if h goes to 0, then h squared goes to 0, and all that's left standing is 3x squared. That's the derivative. Same result as before, which should absolutely happen. It's just different approaches. Okay, so you will have to do some of that on your homework. You should be good on the empty boxes from set 2021 and be able to do those now, I believe. All right. Now, after that, after you're able to do a derivative on your own, you also need to be able to recognize a derivative. Sometimes they're going to have the derivative set up for you, and you need to say, oh, I understand what's going on there. These are all derivatives here. I know they look like limit problems, but they all came from setup derivatives. In each case, I want you to do three things. I want you to tell me which of the definitions was used, what the function is for this specific problem, and is it at a certain number a, or is it just any old x? First thing, all these will come out 0 over 0. It's probably some derivative. If it's h to 0, then it must be either the first definition, or there's a mistake there, or the symmetric definition. If there is no h going to 0, then it's alternate. If x is going to some c, for example, it's alternate. If it does have an h and it has both x plus h and x minus h, then that will help me choose between symmetric or not. All right, so let's go through this here. This guy, it has no h, x goes to 3. That is the alternate definition when x approaches a constant. All right. The function, now it helps to have the derivative definitions to look at, but the alternate definition, the numerator is f of x minus f of 3. Hi. Okay, so alternate definition. Next thing is, what is I supposed to say? What the function is? Well, by looking at f of x here and comparing it to what's here, it's obvious that f of x is just the absolute value of x. And then at what point, the easiest place for alternate is to look here. X approaches a, so in this case, it's x approaches 3. So I'm looking for the derivative of the absolute value function at x equals 3. Can anybody tell me what that would be, just thinking visually? Yes, 1. Absolute value looks like that. If you look at the slope at 3, the slope is just up 1 over 1, so that would actually come out to be 1. Anywho, not part of the question, so don't worry about that. Number B, or letter B here, all right? So again, x is approaching 3, so I feel like, again, alternate definition. It's not an h like over here. Alternate definition if x approaches a number. In this case, the function f of x must be 2 absolute value of x minus 1. And again, I can tell what number by looking here. It must be at x equals 3. That's the idea. Try those on your own. And once you've tried all of them, then push play again or listen to the rest of the recording. But now try the rest on your own. Okay, so if we check out how you did, this has an h in it. So I know it's either first definition or symmetric. Now, choosing between the two, this has x plus h, but no x minus h. That means it's not that symmetric idea of approaching from both sides. It's more like just the first definition of the derivative. Now, in the first definition, you have f of x plus h minus f of x on the top. So in terms of what to look at for what's the function, this time look here. The function is x cubed plus 3x And because it's just generally at x, not at a certain number, it is at any x rather than a specific number. That would be a rule for finding slope at any point. Okay? This is at an ampersand. All right, let's go to the next one. This also feels like it's not alternate because it has h's, and we are therefore looking at the first definition of the symmetric definition. This time we have x plus h and x minus h, but that's a symmetric definition. So that's a symmetric definition. The function is a little harder to tell here because there's no straight up f of x anywhere, but if this is f of x plus h, then what they must have put x plus h in is just something cubed plus 3, and x cubed went in. So I would say the function is x cubed plus 3x. As far as at what point, it's generally at every x, and so it's at any x. It's a derivative rule to be used with any x, not a number, specific slope at a point. All right, go to this guy here. I see h's, and h going to 0, so again I think symmetric for first definition, but it doesn't have x plus h or something, a plus h and a minus h. So it's more like the first definition because there's no plus h minus h. The function and the point, let's take those two in conjunction. I don't see x's here, so it doesn't feel like it's at any x. It's at x equal, and what seems to be putting in instead of a plus h, they have an a of 4. So it feels like the derivative at x equal 4. That would mean then that if a plus h minus f at a, the derivative seems to be, or the function seems to be something cubed plus 3 times the something you put in. So I feel like the function is x cubed plus 3x. All right. Last row. We have h's there, and so it feels like no x, no minus h, so it's first definition. It still looks like no x's, so it looks like at a specific point, it looks like still x equal 4. In fact, this looks very similar, and in fact it is identical as the other one. The only difference is this guy. But really, aren't those the same? 4 cubed plus 3 times 4, that is 76. So it's the same thing. The only difference is it's simplified. Now that makes a little harder because it feels like 76 is out of nowhere, but it'll happen sometimes. That number will be simplified. Get over it. All right, last but not least, this guy. This is the gotcha. Even for you honors students, this might have been tricky. Start with alternate or symmetric. This is x going to 0, not h going to 0. So this is the alternate definition. It seems like then it's at x equal 0. So I'm finding the derivative of this function at 0. Now the question is, what's the function? F of x equals, well, this is f of a plus h, and it feels like, oops, that's not the alternate definition. Sorry, this is f of x minus f at a up here, so it feels like f at x is exactly what I see there. F of x is 4 plus x cubed plus 3 times 4 plus x. Now that was probably a gotcha. You maybe wanted to say that a was 4 again because we've done that so many times, but no, a was 0, and those 4's were actually part of the function. All right, hopefully you didn't miss that one. Now, last but not least, using your calculator to find a derivative. It's hard to visualize the slope. It's a lot of error in that. So your calculator is going to make a calculation by choosing tiny, tiny points very close together. Like in the Inspire, I think they're 100,000th apart or something like that, and finding the slope, and that's where it's going to get its derivative estimate. So when you use your calculator, you're going to get a good numerical estimate of the derivative of the point. The calculator doesn't actually know calculus. It just makes a calculation that it feels is close to the change at the point. And close being like a 1,000th, a 10,000, 100,000, maybe a millionth away. I can't remember the Inspire delta x. All right, now this. If you're to look at this, I hope you look at this now, this limit differently, and think derivative now. X approaches pi over 6. That's the alternate definition. of the derivative, and the function is sine. So this is the alternate definition of sine's derivative. And at the point x equal, well, this is x minus a, so it must be at a equal pi over 6. You could say x equals or a over 6. Now the limit is hard to evaluate because it's 0 over 0, and there's no algebra to be done. So that's hard. We learned that if that's the case, you can use your calculator. Now the calculator actually has a shortcut. It's going to do the derivative calculation. This is how it goes. If you have the Inspire, get your Inspire out, and I'm going to clear the old scratch pad and start fresh. Now, here's how you go about finding the derivative with the Inspire. There are a couple different ways to do it, but the easiest way people find is menu, and choose the calculus menu. Now you're doing calculus. You want the very first option, numerical derivative at a point. Now it's going to start to give you some choices here. In this case, the variable is x. It's sine of x, not t, etc., so it's x. The value is the value at which you want the derivative. Now we set the derivative at pi over 6, so we're going to choose pi divided by 6. And the first derivative, you can actually take the first order, second derivative. We haven't talked about that yet, so let's go with first derivative, hit OK. And this is what you see. Back in the home screen, it pastes this. This means take the derivative of what? It's waiting for you to tell it the function. You haven't said anything about sine yet. It doesn't know you want the derivative of the sine curve, with the slope of the sine curve. So you need to tell it. Trig sine of x at x equal pi over 6, hit enter, and boom, it gives you the slope of 0.866, which is to say that if f of x is sine, if the function is sine, then the derivative at pi over 6 is approximately 0.8660. I should have mentioned this, but I'll mention it again. Remember, there's two notations for the derivative. This is Newton's notation for the derivative. But the other creator of the calculus, the German Leibniz, he used more like the dy dx, which really represents a small delta y over delta x at pi over 6. That's his notation for the derivative. That's the derivative of y with respect to x, or dy dx, at pi over 6 is, and it's the same answer. Okay, it's just different notation. You do need to know both. They're both very handy. So, and you'll see both in any calculus class. Okay, so I'm going to get rid of that. Try one on your own. Oops, or not. Try that guy on your own. Find the instantaneous rate of change at time equal pi over 6 for that function. Now, instantaneous rate of change is verbal explanation, or the same as the derivative. Instantaneous rate of change is the derivative. So when they say instantaneous rate of change, they want the derivative. Notation-wise, you could say p prime at 6. The derivative of p at 6 is how that notation would read, or p prime at 6. Here's your calculator. Okay? We want the derivative. This time it's t. Well, you could use x actually and just pretend they're x's. At 6, and the first derivative. The function they want is 3t minus, log is over here above the exponential, base 4 of t, and enter. And the slope is 2.8797. 2.877. Alright, so that's calculator calculating the slope for you. If it says use a graphing calculator to find the slope, then you may do that. If it says use the definition of the derivative, then you've got to do that. That, I believe, is that. You should be able to finish the empty boxes in set 20 and 21 and be ready to turn that in on Thursday. Bye.